In number 11, they have a trig equation that they want us to solve, and they're giving us a specific domain to solve it over. So we'll worry about that in just a few minutes after we figure out what the sine of 3x by itself is equal to. So the first thing I'm going to do is I'm going to put the -1 on the other side. So in order to do that, I have to add it to the other side, which will give me 2 sine of 3x is equal to -1. The next thing I'm going to do is get rid of this 2 that's being multiplied by the sine of 3x by dividing everything by 2. That will give me the sine of 3x is equal to -1/2. And then basically, like, one way to think about this is say, okay, where is the sine equal to -1/2 on the unit circle? It's an exact value, so we can figure that out. We don't have to use our calculator. So what I'm going to do is just ignore the 3x for a second. I'm just going to say where, again, is the sine equal to -1/2 on our unit circle. That happens to be at 7 pi over 6, as well as 11 pi over 6. And then I'm going to bring down the 3x because that's what we're left with. So basically what I did, I didn't show this step though, is I basically took the inverse of the other side, which is going to give me some angle measure, some radian measure. And I'm doing it in radians because, again, our domain says to be between 0 and 2 pi. So the next thing I'm going to do is pay attention to this domain up here. It tells us that it's 0 to 2 pi, so I'm going to multiply this by 3 because our angle right here, 3x, is being multiplied by 3. So x is our angle and it's being multiplied by 3, so we have to multiply the domain by 3. If we multiply both of these values by 3, we get a new domain of 0 to 6 pi. So basically have to say, okay, well, I'm going to add 2 pi 3 times to both of these values, 7 pi over 6 and 11 pi over 6, because this is like saying that we're going around the unit circle 3 times. Okay? So again, I'm going to add 360 or 2 pi to both of these values to get more values. So if I add 2 pi to this, we could type it in our calculator. I'm going to say 7 divided by 6, and then I'm going to add 2 to that, because I'm adding 2 pi to that. I'm going to leave the pi's out to keep it simpler though. So I get that, and then I can hit math to a fraction, and I get 19 over 6. I'm also going to do the same thing with 11 over 6. And then a little shortcut, I want my answer to fractions, so I'm just going to hit math fraction now. It's going to give us 23 pi over 6. So coming back to this screen, I'm going to have my second set of answers will be 19 pi over 6, and I also have 23 pi over 6. And then I'm going to do the same thing, so I'm not going to show my work this time, but again, I'm going to add 2 pi to this 19 pi over 6. That's going to give me 31 pi over 6. And my other answer, if I add 2 pi to 23 pi over 6, is going to be 35 pi over 6. So basically, again, this is going around the unit circle 1, 2, 3 times because we went from 0 to 6 pi. The last thing we have to do is get x by itself. So we have to divide all these values by 3. Or another way of saying that is just simply multiply by 1/3. So I'm going to take all of these values here and I'm going to multiply them by 1/3 because, again, I want to get rid of this x on this side. We can do that by multiplying by 1/3. If we do that, the 3's are going to divide out and give us just x. So anyways, when we multiply each one of these values by 1/3, we get x is equal to 7 pi over 18, 11 pi over 18, 19 pi over 18, 23 pi over 18, 31 pi over 18, and 35 pi over 18. So here are all of our values for x. So not very difficult, just a little tedious with these end steps because, again, we have to go around the circle 3 times. Okay, so number 12 asks us if the domain of the equation is unrestricted for the equation that we just solved, how many solutions would exist? And then we want to explain our answer. Well, let's see if we can make sense of this. So if I didn't have that restricted domain that was originally, 0 to 2 pi, that we multiply by 3 to get 0 to 6 pi, if I didn't have that restricted domain, it could go from 0 to infinity. So that makes sense to say that we would have an infinite number of solutions. Because and one way to think about it is we would keep going around and around and around the unit circle without stopping, so we're just going to have more and more and more answers. And number 13 says, for what values of y would there be no solution to the equation y equals 2 sine of 3x minus 1. So we don't know what the y value is. So I'm asking, what y values would it never equal? Well, if you kind of refer back to the graph that we graphed in number 10, that I'm going to pull up here on the calculator. If you want to plug this in your calculator to get the same picture I have my mode in radians, and I'm in function mode because I'm trying to plug in a y equals equation. My equation just plugged in what's on the paper, 2 sine of 3x minus 1. I hit zoom, I hit this trig option, which usually works pretty nice, and you get this graph. And again, we graphed this by hand in number 10, which is something required for our final exam, being able to graph it by hand. But you can kind of see that the max value here is 1. The minimum value is -1, -2, -3. So basically our y values are never going to equal anything less than -3 or greater than +1 because the graph doesn't exist there. That's why I had put this note in there to think about the range. So the range is a possible y value. So our answer says, for what values of y would there be no solution? So I'm going to write, one way to write this is negative infinity having trouble writing that. I'll write it on this page just because I'm having an issue with that program. But anyways, for number 13, it would be negative infinity to -3. So basically anything from negative infinity all the way up to -3. And, or I should say union, with 1 to positive infinity, so anything larger than 1. Alright, the next problem, number 14. it asks us to verify this trig equation. So basically we want to make the more complicated side look like the less complicated side. So what I'm going to do is kind of go with that approach I just talked about. I'm going to make the more complicated side, which I think we would all agree is the right-hand side, look like the left-hand side. It's going to be much easier to do that than it would be to try to manipulate the the left-hand side in order to look like the more complicated side. Much more difficult. Okay, so one thing I'm going to do, the first thing I'm going to do is say, okay, well, wait a second. They have -7 here, -7 here. So if we added 7 to both sides, they would just cancel out. So there's a little trick. So that already makes things a little bit simpler. Another thing I want to do is 4x in here. Since it's the same angle, 4 times x in every single function in there, I can just rewrite this with something else. We don't have to write 4x every single time. So I'm going to write the sine of theta equals, I'm going to simplify cotangent in this step. I'm going to rewrite that as a function in terms of sine and cosine. So cotangent is cosine over the sine. And I'm multiplying that by secant of theta. Again, I'm just replacing the 4x with theta because every single function has 4x in it. Secant is 1 over the cosine of theta minus cosine of theta, which is already in terms of sine or cosine. I'm going to distribute this term through to both terms. Well, what happens on the first term? Well, the cosines in the numerator and the denominator here and here are going to cancel. So that's nice. That's going to give us 1 over the sine theta minus cosine squared over the sine theta. I want to encourage you to pause and stop and make sure this makes sense before we go any further. Don't feel like you have to keep rushing through the video. I'd rather you take a minute and make sure you understand what's going on. The next thing I want to do is combine these two fractions. They both have the same denominator, so I don't have to do anything fancy here. I can just simply say the same denominator, so sine of theta under 1 minus cosine squared of theta. And you might start to notice something here. This looks similar to the Pythagorean identity sine squared theta plus cosine squared theta equals 1. Well, if I manipulate this identity, what happens if I put the cosine on the other side? Well, I have to subtract it. So I had the sine squared of theta equals 1 minus the cosine squared of theta, which is exactly what we have here. So what we get is the sine squared of theta divided by the sine of theta. And we know the laws of exponents say to subtract exponents, so we know that this exponent down here has a 1. So 2 minus 1 would just give us 1, or sine to the first power. So we have just regular old sine. And that's exactly what we have on the left-hand side. So once we verify that the one side is identical to the other side by doing a little bit of algebra and manipulation, we are finished. We're all done.